welcome along to my live stream today, and we're going to be looking at electromagnetic radiation and quantum, which is a topic in A-level physics, as I'm sure you know. And it's quite a big topic, so I decided I'll break it down into 2 or 3 lectures, for want of a better word, and the first one of these is going to be on the photoelectric effect. So without further ado, let's jump into that. So if you are going to understand the photoelectric effect, you really have to start off by thinking a little bit about the nature of photons. So that's where we're going to start. Remember 100 years ago when they were kind of discovering the photoelectric effect, they didn't really know about photons in a sense. The idea of photons came out of the photoelectric effect. So in a way we're kind of doing this backwards, you know, backwards to how they did it. So we're in a much kind of stronger place really. So a photon can be thought of as firstly a packet of electromagnetic radiation. Okay, so what do we mean when we say electromagnetic? Well, the clue here is in the name, because we've got electric and magnetic, and what we've really got is electric fields that'll be oscillating, say, up and downwards, and magnetic fields which might be oscillating at 90 degrees to the electric field, like this. So electric fields going up and down, magnetic fields going across, and then the whole lot is coming out of the screen towards you. Very difficult to draw that, but not so bad if you use your arms to illustrate it. Alright, so electric and magnetic fields at 90 degrees travelling. So, but it's as a packet, and sometimes you'll see a packet represented kind of like this, which maybe has its uses, but to my mind is a bit misleading, because what we're suggesting here is that we have an amplitude in our photon that's changing, and I don't think there is any kind of equivalent of amplitude in a photon, and we'll talk about that a bit more in a moment. So if you see that, just be careful with it, that illustration. So a photon, packet of electromagnetic radiation, and it was worked out that the energy of these packets is simply equal to h, which is Planck's constant, multiplied by the frequency that is associated with these photons. So frequency, you know, is measured in hertz, and energy always measured in joules. So we have a little formula there for the energy of these photons. Now, because we say they have wave-like properties, we can say that all members of the electromagnetic spectrum are going to be made up of photons, and are going to follow the little formula that C equals F lambda. Now, let's just say for a sec, the electromagnetic spectrum is that great big family of waves that you talk about over and over again in physics. Radio waves, microwaves, infrared, and so on, all the way up to all the way up the spectrum to gamma rays. And the thing that's different, really, is, for us anyway, that we're concerned about, is the frequency. So they all travel at this amazing speed of 3 times 10 to the 8 meters per second, which is rather oddly called c. Who would have guessed that c would be the velocity of light, or the velocity of electromagnetic photons? Anyway, there you go. It is. So we can take this little formula, rearrange that to get C over F lambda, and then chuck that into our formula for energy over here to get that E equals hc over lambda. So these are 2 ways then to write out the formula for the energy of a photon. And yeah, just one thing to say. So one other thing is that this is a bit odd really, because if you think about a sound wave, if you want to give a sound wave more energy, you're going to turn up the volume, aren't you? You're going to make it louder. And what you're doing there is you're changing or increasing the amplitude of the sound wave. But that's not the same in light. That's not the same in electromagnetic radiation. There is no equivalent of an amplitude. So it's a different beast, this one. Alright, so there's a quick, basic, flyby introduction to photons. So, photoelectric effect then. So this is basically a situation where you get a bit of metal. It might be, I don't know, calcium. It might be potassium. Well, probably not potassium. It's quite reactive, isn't it? Calcium or some other metal, lithium perhaps, etc., etc. And you irradiate this metal with a member of the electromagnetic spectrum, and then, hey presto, hell surprise, electrons are emitted from the surface of that metal. Lots of these, but not all, but most of these electrons have a significant amount of kinetic energy. And the mere fact that if you turn off this radiation over here, you get no electrons, and then you turn it back on and you get electrons with kinetic energy, is a pretty strong indicator that these electrons are coming out from the surface of the metal because of the radiation. Let's just bring up the chat. So it's a pretty strong indication that the photons are causing the electrons to be emitted there from the surface. So that's the first thing. Now, at this stage, as good scientists, you might say to yourself, well, we need to investigate this. So what could we investigate? Well, obviously we could change the metal if we could think of any. So we've got calcium, lithium, lead maybe, I don't know, a whole pile of metals you could use. Well, but we'll keep the metal the same. So what we can change relatively straightforwardly is the frequency of that radiation. And then we can measure the number of electrons that we get and obviously the size of the kinetic energy. Now, at this stage in a kind of a talk or a series of lessons on the photoelectric effect, you'd probably get a load of stuff about how the threshold frequency, what the threshold frequency is and how it works and so on. But I'm going to take a slight detour at this point and talk about how this kinetic energy is actually measured, since it comes up in questions I've seen, and also I think it gives you a bit more understanding of what's really going on. So this is a piece of apparatus or a setup that you might use to measure this kinetic energy. So here we have some radiation coming in, and this curved plate is our photoemissive surface, which is a way of saying it's like the calcium or whatever it is. And you'll notice it's curved. Then the whole thing is inside a glass tube, and so this glass, and then inside that is a vacuum. And yeah, so that's that. Then down this end we have an electrode there, which is connected to a battery, which is variable. Now the main thing to note with the variability of this is that you can swap the battery around, as it were, so it's the other way around. In other words, you can change the polarity of it, so we can make this electrode positive or negative, as well as changing the magnitude of the voltage there. So we can measure the voltage across the electrodes, because after all, the electrodes are connected straight to the voltmeter like this, so they are in fact measuring the same thing. Let's get rid of those yellow lines, and we can measure the current. So here we have a nice little setup to measure the current that's going to flow and the energy of the electrons, as we'll see. So how does this work? Right, so let's go into a bit more detail here. So I've simplified version of the diagram here. Let's say, just for the moment, that this is going to be, that pen's no good, is it? 0 volts. What that means is that there's 0 volts on both of the electrodes in our setup, which means that the voltage between these two, well, guess what? That's 0 as well. So we've got no potential difference shooting electrons across here. So we then irradiate the surface, and Johnny Electron sitting here, we won't worry about the threshold frequency or any of that stuff at the moment, receives enough energy to kind of zooming off like this. So he's going to travel all the way across here and go bang into that electrode on the other side there. Now if that happens, what we're doing is pushing an electron on here, and because all this is in series, it's like a little circuit, isn't it? An electron has travelled from this point way all the way over to that point. In other words, we're going to read a current. Now what happens if we make this voltage positive? So let's just say it's positive 1 volt. Now you know that these electrons are negative. Well, I hope you do anyway. Which means that as this electron comes flying off, it's heavily attracted to the +1 volt. Therefore it accelerates and ends up at the electrode going nice and fast, handing over a pile of energy. So far so good. Right, well now let's make that voltage negative. We're going to say this is -1 volt now. This is where it gets a bit more interesting, because now as our electron travels over, it's going to experience a repulsive force, and that repulsive force is actually going to get bigger and bigger and bigger as the electron gets near. So we now have a repulsive force, if you like, pushing back on the electron. Now let's put some numbers onto this now. What we're going to do is I'm going to assume that this electron comes flying off with 2 electron volts of energy. All right, so off it comes, zoom. That kinetic energy, half mv squared. Now if this voltage over here is still -1, that means that potential difference between these two plates is -1. Now That means that in order to get an electron to go from 0 volts on this side to -1 volts on that side, we're pushing against the repulsive force. The electron doesn't naturally want to go in that direction anymore because it's being pushed away. So obviously the electron's going to slow down a bit. And it turns out, because this potential difference between the two electrodes is 1 volt, we're going to need 1 electron volt of energy to get the electron across the gap. So the upshot of all that is that since our electron has 2 eV, it's going to lose 1 eV getting across, but it's still going to arrive and we're still going to get current. Okay, and the reason for that is because the energy of the electron when it's emitted is greater than the energy needed to get across the gap. So let's take this a bit further now. What if we change this voltage now to -3 volts? So make this -3 volts. That now means that in order to get the electron from the curved electrode to the ball electrode, or to the cathode, we're going to need to use 3 eV. But our emitted electron only has 2 eV, so it will do something like this. Curve away because the repulsive force is so big. Or the other thing it might do is come in, stop, turn around and come back. It depends exactly at the angle that the electron's arriving, or approaching perhaps I should say, with. Or in other words, what's going to happen is that our photoelectron that's emitted is not going to get to the cathode. So there's going to be no current in this case. Now where this gets really interesting and really useful is that you can, let's consider what happens now if we have a number of electrons coming over. So this time we're going to have a little blue electron that is emitted with 1 eV and a red electron that's emitted, say, with 2 eV, and that is, this red one is the maximum energy. So this is EK max. So what we do then is we vary the voltage on this. Let's say we'll go from 0 and we'll vary it down to, I don't know, let's say -3 volts. Now what we'll get then as we do this is a little graph like this. So here's current in the ammeter, and along the bottom we've got voltage. So when we've got 0 volts, both those electrons will arrive, and so we'll have a nice current. As we increase this voltage, let's say we've got -0.5 now, both electrons are still going to arrive, so that current value is going to stay the same. When we get to -1 volt, one of our electrons isn't going to arrive anymore, so the current will now drop. When we get to -1.5 volts, we'll still find at that point that our 2 eV electron will arrive, but our 1 eV won't, so the current will do this. And then when we get to -2 volts at this point, that current will suddenly go to 0. Now obviously I've only shown 2 electrons. You won't have 2 electrons, you'll have millions of electrons. So what you will get is actually a rather fine curve, something like that. And at this point here, let's make that blue, at that point there where the current becomes 0, that is the point where you have just stopped the most energetic electron. In other words, you have measured the kinetic energy that the fastest electron that leaves the surface of our metal has. So that is our value for EK max. Now that's going to be really important to us as we get into formulas in a few minutes. Okay, so let us move on. We'll now go back to the effective frequency and that kind of stuff here. So I just need to reset my screen for some reason, so we'll just bring that back. Just bear with, I will only be a second or two. Okay, so we are going to be here now. Still hasn't reset. There's so much to think about here. It's so difficult. Yeah, excuse me moaning. Why is that doing that? Right, back. I'm just going to move that slightly. Right, so we're back. Sorry about that little delay. So now we're going to look at the effect of the frequency in a little bit more detail. And this perhaps might be the stuff that you expected that I would start off with. So what we're going to do is we're going to change the frequency of the incoming photon and think about what's happening to the electrons that are emitted. So first of all, we're going to start with a low frequency. And what you find is that what is emitted is absolutely nothing. And it doesn't matter how long you wait, nothing carries on being emitted. Nothing. Then you get to this magical point known as the threshold frequency, often written as Ft. What happens at this point is that electrons start to be emitted. And then if you keep increasing the frequency over to here, what you now find is that electrons are emitted just like they were before. But there are some differences. So let's look at what those differences are. So what's happening here is that we are increasing the frequency. So when the frequency is below the threshold, absolutely nothing happens. When the frequency is at the threshold, what happens is that an electron literally just goes pop, comes out of the surface and literally hangs around just outside the surface of the metal. In other words, it has zero kinetic energy. Alright, so there's no kinetic energy. As you increase the frequency, you find you get the same number of electrons that are emitted, but the value of EK max, the fastest electron, increases. Now what we're saying here, in this case where the frequency is the threshold frequency, EK max, this might seem a bit strange to write this, but EK max is actually equal to 0. Has no kinetic energy because, well, there is no kinetic energy. As you increase the frequency, so the kinetic energy goes up. Now, there's an interesting thing here, because what happens if you were to have a frequency, just say here, just below the threshold frequency, a tiny little bit less energy than you would need? What would happen then if you irradiated the surface of the metal with, say, a frequency 2 hertz below the threshold, and you waited, and you waited, and you waited? And the answer is nothing happens. You still don't get an electron. Now that's very odd, because you know that waves deliver their energy continuously. Now you know this is true because if you think of, say, a cliff at the sea, on the beach or something. I used to go to this beach a lot when my children were younger, and I went back to it sort of 10 years later after they'd grown up a bit, and a great chunk of the cliff has come falling down. And that's because of the regular, steady energy that's delivered continuously to the cliff face by the waves. Gradually, they just wear it away. Energy is delivered gradually by waves. So you would think if these photons were acting like a wave, then a little electron down in this surface here would pick up some energy from the first photon, and then pick up a bit from another one, and pick up a bit more from another one, and eventually get enough energy to escape. In other words, the energy would build up. But that doesn't seem to be what happens. So this is really strong evidence that these photons are not behaving like a wave. Let's go on and look at a bit more. What about the effect of intensity? So what that means is making this brighter. So intensity, as you probably remember, is a measure of energy arriving per second per meter squared. So it's watts per meter squared. So we're increasing how much energy is going, but we are keeping F, very important, the same. So we're not changing the colour, in inverted commas, of the light. What happens if we do this? First of all, what you notice is that you get more electrons emitted. That's the first thing. Okay, so that implies that more of something is arriving here. But strangely, what you find is that EK max, the maximum energy, for each of the photons remains the same. In other words, there is no increase in kinetic energy like you would expect if you put more energy onto a meter squared. Again, very strange conclusion this. And what this leads us to suggest is that, well, let's recap first. So let's recap what we've learned so far, because there's a lot of stuff going here. So we've introduced this idea of something called the threshold frequency. I'll just come back to this in a minute. We've said that the electrons are emitted with a range of kinetic energies from 0 to some maximum. We've said that if you increase the frequency, the kinetic energy goes up, but you don't get any more photoelectrons. We said that the amount of time you leave the radiation makes no difference. And we said that if you increase intensity, you get more identical photons. But we haven't really mentioned this work function thing. So now might be a good time to do it. So work function, given the symbol phi, so that's another Greek letter, is the minimum energy required for an electron to escape from the metal. So if you like, if you imagine your metal surface here, here's an electron, we're thinking about the energy, because remember the energy coming in is given to helping the electron to escape, and also some kinetic energy. But if we set that kinetic energy to 0, in other words our electron just goes pop and sits outside the surface like this, then the amount of energy we needed to get that electron to escape is the work function. It's the minimum energy needed for an electron to escape. Okay? Now, all of this leads to this famous expression that physicists like to use, a one-to-one interaction. So what this means, what is going on here is this is not wave behaviour. This is particle behaviour, although even that is slightly weird, as we'll see. So what we're saying is that we have one photon is giving all of its energy to one electron. Now, it doesn't have to be an electron, but obviously in the photoelectric effect, it is an electron. It could be some other particle here. So the strange thing here is that you cannot absorb part of a photon. Now, this is strange, and it's not like particle behaviour, because if you imagine your friend, there's your friend, and you throw a tennis ball at your friend's head. I'm sure you've done this. I know you're saying you haven't, but I bet you have. Okay, so this tennis ball might come in with a measly 10 joules of energy, and then it's going to bounce off your friend's head, and it might only have, say, 8 joules of energy. How does your friend know that you've thrown a tennis ball at them? Basically because it hurts. And how does it hurt? Because they've received some energy. So when a tennis ball hits your friend, a tennis ball is clearly a particle, but it is not undergoing a one-to-one interaction with your friend's head, because the tennis ball firstly still exists. There it is, it's got 8 joules, and it hasn't given up all its energy. Now photons aren't like that. If you have a photon, how do you draw a photon? Well, let's just draw a photon like that, and then you interact that with an electron. What happens is the photon comes over. Let's say it's got 1 joule of energy, stupid number, but let's just pretend, okay? The photon hits the electron and completely ceases to exist. It disappears. Goodbye photon. And the electron has gained that 1 joule of energy. Now, we need to be careful with this little diagram that I've written here, because there are all sorts of ifs and buts about it, as we'll see. Okay, so this photoelectric effect is explained to a large extent by this idea of one photon giving all of its energy to one electron and ceasing to exist. Right, so now the nitty gritty. We'll get right down now into the structure of what's going on in the photoelectric effect. So here we go. You have learned over and over again in your school careers about the structure of metals. I kind of feel that a good proportion of physics A level is explainable by talking about structure of metals. So very quickly, here's the surface of a metal. Surface. And we've got a number of ions here. Positive centres, and there are electrons that are bound to these ions. I'm not going to draw them all. All right, so the blue ones are bound electrons. They play no part at all in the photoelectric effect. Now I'll stress that because I regularly see students describing the photoelectric effect, talking about energy levels. You know, those energy levels. This is a subject from my next video on this stuff, that go like this and the electrons jump up and down. That is referencing bound electrons. The photoelectric effect does not involve bound electrons, so forget them. At the same time though, we have our old friends, the delocalized electrons, that are just sort of hanging around in the structure. Now these things are not still. Normally speaking, with your metal that you have on the desk or whatever, these sea of electrons, these delocalized electrons, are just whizzing around. They've got some kinetic energy and they're colliding and whizzing. Okay, right. Now, if you then shine in some radiation, so here's a photon. This photon, it doesn't really know about the surface of the metal because, you know, it's so flipping small. So I'm going to move that photon. What we'll do is we will have a photon coming in here, and I'm going to put this electron, this delocalized electron, right at the surface. So you'll be clear here about, you know, what sort of dots we're looking at. Okay, so this one here is a delocalized electron, and the blue one here is a photon. The photon comes in, collides with the red electron, and we know that it's a 1-2-1 reaction. So all the energy of the photon is absorbed, and this little red electron now finds itself, it says, I've got extra kinetic energy. So it's whizzing around faster, and it's whizzing around fast enough to be able to break the bonds that bind it into the metal, because even though it's delocalized, these electrons are still, you know, attracted and bound into the structure. However, this one's gained enough energy to just plop out. So it comes out, and it's going to have some EK as well, probably. Okay, because this is the one that's right at the surface. Now you've probably come across that a lot of times. Now let's consider a second electron, delocalized electron, right down in the metal here. Now I've only drawn it 2 layers, but obviously it's a lot further. In comes a photon. It's missed all this lot, so it's travelled through the structure, and it arrives at our little delocalized electron right down deep in the metal there. It hits that delocalized electron, ceases to exist, goodbye photon, and gives all of its energy to this delocalized electron. So this one here is now all excited. It's gained some extra energy. And so what does it do? It whizzes around. But they're already whizzing around, aren't they? Remember? Look, they're already whizzing around. But this one whizzes around a bit faster because it's got more EK. So it carries on whizzing around and does some collisions. So here it is, colliding around. And by the time it gets up to this point here, say, it's done, I don't know, 1, 2, 3, 4 collisions. Well, 4's not very many, is it? But it may be more than 4. I'm just making numbers up. So it's done 4 collisions. In the process, it's lost a load of the energy that it gained. It's now back to what it normally was. So when it gets to the surface, it hasn't got enough energy now to get past the work function. So this poor little electron here, it spent the time being all excited, but it's given up its energy that it gained from the photon to the surrounding ions in the structure. So it doesn't escape. But there are going to be some electrons that are going to be not as deep as this poor little one here that's lost all its energy in the structure, so that they bounce around, but when they get to the surface they still have enough energy to get out. So let's ask ourselves one more question about this. I think you'll see where this is going. If we take this first electron here and another one down here, let's call that electron 2, and one more that's down here, electron 3, all 3 of those electrons are being irradiated by the same amount of energy, E equals hf. Let's just say that's 2 joules. I mean, stupid value, I know, but let's just say. So each electron, 1, 2 and 3, gains 2 joules. If the work function is, I don't know, let's say half a joule, then electron 1, it's gained 2 joules, it's right at the surface, so, it flies out, and electron 1 will have an EK equal to, in this case, 2 minus half, because half is the work function, 1.5 joules. It's happy, it's escaped. Electron 2, though, is going to do a few collisions before it gets to the surface, and it will have lost a bit of energy. So instead of the extra 2, it might only have an extra 1. It then loses another half to get through the work function. So electron 2 will lose 1.5 joules, which means it will come out with only half a joule. Now electron 3 is going to have a whole load of collisions before it gets to the top. It's going to lose all its 2 joules that it's gained from its photon. It's got no chance of getting out. So now you can see why we have a range, and hopefully you can see that the ones at the surface, i.e. in our case electron 1, is going to leave with the most energy. And that's why we get a range of energies coming out through these photons. Okay, so we're almost through this. This then leads us nicely to our formula, and this of course is the basis of most of the questions that you're going to get in your lovely exams. So we have a formula here, E equals E equals E, because this is an energy too. Now this is a silly thing I just said really, because any formula, all the things have to have the same units, otherwise you can't add it up, can you? So all of these are joules. So I find one of the issues here for students is getting confused between what all these various E's are. So in a way, EK max is fairly obviously, it's the maximum kinetic energy. Phi, the work function, is really straightforward too. But E here, this is the energy of our incoming photon. So that's the energy of our photon, and this is the energy of our photoelectron. Oh, in other words, the electron that's been emitted, the photon that's coming in. So we could rewrite this as HF equals EK max plus phi. Maybe that's a bit easier to use. Right, so that's a whiz through the photoelectric effect, and hopefully it was useful. I don't know if anybody's watching, but if you are, some questions would be nice. And so I've got a couple of questions that I'm just going to look at. I might just look at one, to be fair, for now, since it's gone on for half an hour. So let's look at this first question here. So this is a typical, what am I trying to say? This is your typical kind of multiple guess question here. And it says we have some photons of a wavelength. Notice they'll do this. They'll give you wavelength and not frequency. They're incident on metal plate. The work function is EV. Notice we're in the realms of EV there. That's good. What is the maximum kinetic energy? So we want EK max, EKM. That's our goal. So we know that E is going to be equal to EK max plus phi. Well, we know phi. We know EK, actually, we want to find this, and we can get that because we've been given lambda is 290 nanometers. Right, but we also, so we could just use the formula that we looked at, you know, right back at the start of the session when we said that the energy, oops, my pen's gone, now it's back, that the energy was in fact equal to HF, and C over lambda equals F, so the energy is going to be HC over lambda. So if we put in the numbers for that, 6.63 times 10 to minus 34, that's H, times 3 times 10 to the 8 over lambda, 290, and a nanometer is times 10 to the minus, oops, 9. So I put 19 there because I was thinking of something else. I was thinking ahead, but it's minus 9. So work that out, and you will get about 4. No, you won't. You'll get about. What's that? Just can't quite read my own writing here. You will get. I need to just check what that value is. That value is going to be 6.86. This comes out as 6.86 times 10 to the minus 19 joules. It's joules. It's always in joules. But of course that's a problem, isn't it? Because we don't want it in joules. We need it in electron volts because we're given electron volts here and all our answers are in electron volts. So to convert this number to electron volts, we have to just divide it by 1.6 times 10 to the minus 19, because 1 electron volt is 1.6 times 10 to the minus 19 joules. I find this is one thing that divides students. You either understand this or you don't. And so I think this will make a good little session on its own at some point, getting our heads around electron volts. Anyway, leaving that to one side, when you work this out, you get about 4.3 EV. So now we can go back to our formula. We now know the work function, it's 4.1. We know the energy coming in, 4.3. Therefore, we can get EK, which for me has come out as 0.2. So we're looking at A. We're looking at A. Okay, next bit. So this is a wonderful question that came up on one of the papers a couple of years ago. And there's an awful lot to this question, but there's just a couple of bits I want to look at to just make sure that we've got our heads around them. So we have a similar circuit to the one I've been drawing. Notice the curve surface there on our electrode. So very sensitive ammeter, voltmeter, variable voltage. Notice it doesn't say anything about positive and negative. Okay, so this apparatus is used to measure the current that's flowing as you change the frequency or with a particular frequency. Now I'm going to rephrase that. This circuit is used as an attempt to work out what's known as the stopping potential, and hence to get the maximum value for the kinetic energy like we talked about at the start. Okay, so first thing to note is that if you have a curved surface and you irradiate that, not every photoelectron is created equally. Now you know this is true because we've talked about this slide here in some detail. So not only do the electrons arrive at the surface and get emitted with different velocities, they're also going in different directions, which I guess is another way of saying different velocities. So, and that's because they've had a whole pile of collisions before they come out, so they're all moving in different directions. So that means we could represent our electrons coming off of this surface something like this, a whole range of different directions and velocities, and that's the key to this graph here. So the first part that you have to think about is, why is it that the graph goes flat along here? Now this is representing the maximum current. What's the voltage? Well, notice that the voltage is positive. So on our little electrode here, we have an increasing, see how it's increasing, positive voltage. Now all the electrons that come flying off of the photoemissive surface are naturally negative, and so they are going to be attracted towards the anode. But when the voltage is small, say here, like what's that, about, I don't know, just less than a quarter of a volt, some of these electrons will be attracted, because they're moving quite slow, they'll just curve and arrive at the electrode. But this one here, it'll curve a bit, but it's not going to curve enough to arrive at the electrode. So this means that the current is not maximum because some electrons are not arriving at the anode. But if you keep increasing this voltage here, eventually you reach a point, which is in this case around about half a volt, where every single electron that is emitted is curved enough to arrive at the electrode. So that means that if you don't change the intensity of the radiation up here, the radiation that's hitting the metal surface, you're not going to get any more electrons off. As long as you keep that fixed, the number of electrons coming off is fixed. Remember, if you change intensity, you get more. So you must keep the intensity the same. However, we've reached a point where every electron is now being attracted over to the positive plate. So that's why we get a flat, so we get a maximum current. So what happens at the other side of things then? So let's redraw this diagram. So now we've got 0. Let's go back to having 0 volts here. So we're getting around about 26 microamps. So small current, as I said, arriving at the plate there, which implies that quite a lot of electrons are missing the plate. Now, if we make this negative, so let's say we go down to minus 0.5 volts. So now we're here. What's happening now is that the really small velocity electrons that were hitting the plate are now curved away and are no longer hitting the plate. And as we make this more and more negative, so fewer and fewer electrons have the energy to overcome the repulsive force and arrive at the plate. And so eventually we reach the happy point, the stopping potential, where the very fastest electrons are now repulsed and don't arrive. And if they don't arrive, then we get no current at all. So that's what's known as a stopping potential. It's where you have sent away the fastest moving electron. Now that means, in our case here, the stopping potential is minus 1.25 volts. So that means that each electron has to have enough energy of 1.2 or so I'm going to say that again. This means that our maximum energy for an electron is 1.25 electron volts. That's why electron volts are so flipping useful, because you can just take the potential through which they're accelerated and type EV next to it, and that gives you the energy that that electron has. So the maximum kinetic energy in this setup is 1.25 EV. Okay, well, we're at the end. That's it. I've finished. Ta-da! That's my first ever live stream. Finished. So there's all sorts of things I would do differently if I did that again. So I hope it was useful.